like a $200 kit. Like,
Oh, yeah.
model kit enough of,
I mean,
some
but
weird-
with nitroglycerin, I don't think we're gonna be even needing that much. Like for a little can, like,
it's a little thing and it's gonna be like.
and also the synthesis that I found for them was supposedly 94% yield. So it seems pretty reliable.
As you might expect from most humans, one of the first things they do when they discover a new weapon of destruction is optimize it.
Right, yeah.
So picric acid actually, was the initial replacement for nitroglycerin. So nitroglycerin, what they call gun cotton, were available as explosives before that. But the problem with nitroglycerin is that you couldn't use it for explosive rounds and for artillery, because if you did that, it would detonate the explosive round in the barrel because it was too shock sensitive. So the picric acid was an improvement on that. But if you look at the structure,
Oh, wow,
it's basically trinitrophenol.
that's
It's
very acidic.
It's very acidic and trinitrophenol is TNT, trinitrophenol was more explosive. So it's a better yield as far as like how much rust you can get from it or how much explosion you can get from it compared to TNT. Not as good as nitroglycerin, but it was more stable. TNT was the replacement for picric acid in like 1902. The German, that's the numbers I found from Wikipedia.
When Mr. Nobel.
Well, yeah, and they were able to start putting TNT in artillery shells in
That's something gnarly.
right, so the general gist of it is you want something explosive that's shock sensitive enough that when your artillery shell hits, it explodes, but not so shock sensitive that when you launch it out the cannon, it explodes.
Yeah.
Right.
And picric acid was better than nitroglycerin, but it still had it had non-zero chance of exploding in the barrel. Which, being an artilleryman in those days was not like the safe and easy job. So, I don't know, but this one is gonna be the one that blows up and destroys everything around me.
Right, go.
So flying question.
Exactly, so, that's why that Reddit post, the very first thing they say is get a bomb squad to get rid of it, because it's not just that it's acidic, it's that it's shock sensitive and very explosive.
Because I saw that it's supposed to be kept in around like 5 to 15% water.
If you want to keep it, that limits how shock sensitive it is, because the water basically acts like a shock absorber.
Yeah.
A little bit, and it also has a high, you're less likely to have a chain reaction when water's involved, because water's got a high enough specific heat that it stops it from igniting the next step, So.
When I saw that Reddit post, I was like, wow, this shit must be like gnarly.
It is, and the other thing is, because if somebody just happened upon it in their basement or something, odds are it's been there for a very long time, and a lot of these start crystallizing and start decomposing into things that also can start off that process as well and become even more shock sensitive. The fresher they are, generally, the more stable explosives are. So definitely a case of, and plus, if you happen upon a bottle of picric acid in your basement that you didn't even know was there, who knows what else is in there? Right, it's probably best to call in professionals.
Or say like you're in a mine and you find in the whole thing of dynamite, that would be TNT.
Right, exactly.
That would be more explosive than the rest.
So what starts happening with TNT, what makes dynamite safer than just pure TNT is they literally just soak sawdust in TNT and then they bind it up in paper.
Gotcha.
And so what starts happening with old dynamite is it starts basically kind of percolating outward and crystallizing on the outside, and then you don't have that sawdust to act as the shock absorber either. So they get more shock sensitive the older they get in that case too. That's when they talk about it being crystallized, it's basically that it's crystallizing away from the stabilizer, which makes it more dangerous.
Don't keep that going.
Yeah. In general, like, they still use dynamite for some stuff, but they're way better at stabilizing it these days as well. It's basically the form of dynamite they use now doesn't use sawdust, it uses other stuff, it still uses TNT in a lot of cases. Especially if you want to be able to, I know that they use it a lot for ski patrol, for adding control, right? But they're using a version of it that's not nearly as shock sensitive, that basically needs the heat.
Yeah.
And that's why they can light it, throw it, and get away, and so it works okay. Most industrial applications, right, yeah, don't fall. Yeah, exactly, they don't want that to happen, or to set anything off. I think most industrial applications have switched mostly to plastic explosives that need an electrical charge to go on. Because then you don't need to worry about fire, and you don't need to worry about shock. If you don't have the electrical ignition, then they're basically totally pretty much inert. C4 is the military grade version of it, but they have other versions that are similar, that they're soft.
Yeah.
And that may pretty reliably for electrical charge. Yeah,
Really are escaping here.
but it's fun to think of, like, this is something that people spend an entire career on, right? So it's kind of fun to dip into it and see what's going on. I think David asked a question about other protecting groups. There are not any protected groups I can find easily that where you protect a halide, but generally speaking, halides are not a functional group that you need to protect. Because usually the whole point of putting a halide on something is that it's a good leaving group. So unless it's something like a pharmaceutical, and typically what you do is you just put the halide there last. That's your last step because it's the most reactive group usually. But we touched on an example of a leaving group for alcohols. But if you basically do a little bit of research, where did that? Oh, sorry, not leaving group. Protecting group, thank you. This one. Basically, you just get, different types of protecting groups based on what type of functional group you're trying to protect. So if you want to protect an amino group, you can use all these other ones. We actually use the carbamate in lab to make those carbozones. That is a protecting group. It's also a derivative that makes it really useful for finding melting points, which we use it for, but it's also a good protecting group for amines, period. But so carbonyls, carboxyls, a carboxylic acid, what protect a carboxyl group, there's different functional groups. There's hydroxyls, and then there's actually subcategories of protecting groups. If you have a 1,2 diol, a diol where they're right next to each other, there's one functional group one protecting group that can protect both of them. It basically causes both of them to react to make some sort of ring structure. And then there's 1,3 diols have their own protecting groups as well. And so this is a whole bunch of synthetic chemistry research and practice and trial and error that goes into figuring all this out. And it's basically, there's so many moving pieces with some of these compounds that they're trying to synthesize that you wind up, it really is you wind up being very, very specialized as a synthetic chemist because there's so much out there. I had one of my professors in undergrad specialized in fluorinated alkenes. Fluorinated alkenes was his research area that he spent his entire career just in that little niche. Yeah, so stuff like that, it gets very, very specialized, the further you go, and we're starting to see some of that. And then I also double checked our other textbook, our newer textbook, the OpenStax one for non-chromium options, to oxidize the primary alcohols all the way to carboxylic acid. You don't get as great yields, but you can use potassium permanganate, which is really cheap, really ubiquitous, you can find it everywhere, we have a bunch of it in the lab. It has decent yields, I mean, 93% is a pretty good yield. It's not as good as a chromic acid, but then we don't have to deal with how toxic chromium is, and I was looking into the chromium some more, it's also flammable. Chromium-based compounds also tend to catch on fire. And now you're producing smoke that is also incredibly carcinogenic and toxic to breathe. Which I heard there's a new, so we talked about Aaron Brockovich last time. There's a new Netflix series about a similar situation in England, in the UK, called Toxic Town. It's a mini series, it looks like, and it's also based on a true story. I have not seen it yet, so I can't vouch for how good the chemistry is in it. But if you're interested in that sort of environmental policy and those kind of lawsuits and things like that, that's a pretty good place to start. There's lots of good kind of true crime-ish stories about that kind of stuff. There's one in Africa, I'm trying to think of what it was, what the name of the movie was, that also looked at environmental pollution.
I think there was one documentary where it was just a big, it was like a humongous town where it was only like computer waste and like tire waste.
Yeah, tire waste is really bad too, because it's the original microplastics, right?
Yep.
And they to give the tires the right characteristics, they use some pretty nasty stuff that can wind up. The other class, the example that they actually got, any of you heard of the Superfund? It's that basically the EPA was founded as a result of a toxic waste dump in Love Canal in New York. It's one of the, in the east and the northeast, there's all these canals that link all the different lakes together so you can move stuff around. In the town of Love Canal, I want to say it was Dow or DuPont, one of the big chemical producers, was basically just putting all their chemical waste that people were paying them to dispose of. They were just putting it in 55-gallon metal drums and burying it.
Sounds like DuPont.
Yeah.
Is this the Simpsons three-eyed fish?
It's where that.
It's the same plot, yeah, okay.
And so it got so bad, and it was like an Aaron Brockovich situation where there's all these birth defects and super high cancer rates in the surrounding area. And then, but you know what, it wasn't Dow DuPont, it was the company that did it had gone out of business.
Oh, yeah.
And so they went out, and so then there's nobody who even knows it's there. And so they established this, they called it the Superfund, that EPA basically got a ton of money from all these toxic waste producers. That basically they had to put all that money into the Superfund so that the EPA could go in and clean up their messes after the fact. It was a way to keep the cost from getting all the way to the taxpayer, keeping it on the chemical companies to some extent. That's gone away a little bit. But if you hear the term a Superfund site, it basically means that they found toxic waste that needed to be cleaned up, and the EPA goes in and does all the remediation and stuff that goes along with that. It's really interesting. It's right where environmental science and hydrology and chemistry, environmental policy all really intersect, and where they really took off was in the 60s and 70s as a result of Love Canal. And so that's also why we're trying not to use chromium. Last question here. Will primary alcohols always produce aldehydes or carboxylic acids during oxidation, or are there instances where this is not the case? There are oxidation reactions that produce other functional groups, but the easiest and most most well understood ones, usually if you're trying to do something like that, you do it in 2 steps. You make your carboxylic acid and then you convert your carboxylic acid to something else. I don't know of any reactions where you can go all the way from primary alcohol like to acyl chloride in 1 step. You would usually have to do that sequentially, as far as I know. But I had not actually thought about that question because oxidation is, it's oxidation, you add oxygens. But yeah, in theory, you can oxidize by adding anything more electronegative than carbon. So technically, even something like an addition reaction, where you're adding a nitrogen to make an amine, technically that's an oxidation as
As
well,
long as it's on that same carbon.
as long as it's on the same carbon. Typically, what we consider oxidations are mostly alcohols turning into carbonyls or carboxylic acids though. So this is that review slide, I actually updated some of the other figures from the other textbook. So a secondary alcohol to a ketone, you can use chromic acid or dichromate, but you can also use DMP, that desmartinuridenate, and do that more environmentally friendly way and still get decent yields. However, this reaction, the only example I can find of phenol being oxidized to benzoquinone uses the chromium. So there's still a need, as far as I can tell, for chromium on some level in this, if we're trying to make benzoquinone. Or if we're trying to do that test, that qualitative test I was talking about, we want to know what type of alcohol we have. Dichromate is still probably the best option for that. So the advantage, if you're doing things qualitatively, you're doing things on a small scale, so it makes it a little bit easier to control waste. If you're trying to go primary alcohol all the way to a carboxylic acid, KMNO4, potassium permanganate. Otherwise, the DMP reaction will stop at the aldehyde. Right, so we have a pretty good control from the oxidation standpoint. We don't have a great control on the reduction side because we're either using sodium borohydride, which can't do anything with a carboxylic acid. Or we're using lithium aluminum hydride that takes it all the way to the primary alcohol. But if we wanted to start from, say, decanoic acid and turn it into the aldehyde, we just do it in 2 steps. Reduce it all the way back to decanol, and then use DMP to take it to the aldehyde. And we now have enough options with our reactions, we can kind of get around a lot of those limitations. All right, so questions on oxidation reactions? All right, then let's talk about ethers. So ether, the rest of this lecture, I think, is ethers. It says oxygen containing groups, but the next biggest group after alcohols is ethers until we get to the acid derivatives. And then we'll talk a little bit about thiols and thioethers, which is just the sulfur equivalent of these functional groups. So ethers are still an oxygen bonded to a carbon, it's just instead of being an OH group, we get an oxygen in between the 2 carbons. And there's lots of ethers present in biochemistry and in nature. Morphine's an example, melatonin is an ether, even glucose when it's in its closed spring structures is a cyclic ether. So they show up all over the place. They're not usually the most important functional group. If there's more than one function, because we're pretty much always going to name ethers as a prefix. And remember, whatever we name as the last thing we say is the highest priority for these functional groups. And pretty much all pretty much all opiates are gonna wind up being a very similar structure. They all have this four fused rings together, with this bicyclic structure across part of it. And I believe they all have that oxygen there, or at least most of them do. I have to double check to see for sure, but they're all very similar in their structure. Right, so the common names, old school names for ethers, you just name each side like it's a branch. So if you have an ethyl group on one side and a methyl group on the other, that's an ethyl methyl ether. Easy enough, as long as you don't have any other functional groups around. Or anything that's too complicated of a branch. If it's a symmetrical ether, then you would just use di. So diethyl ether, dimethyl ether. Diethyl ether is the one that got used as an anesthetic in the Civil War, until they discovered morphine and opium, or figured out how to purify it for pharmaceutical use. The systematic way of doing it though, is we just name an ether as a branch. It's just instead of putting it as an alkyl group like methyl, we just put that oxy part on there as well. So you get an alkoxy substituent instead of an alkyl group. So if your smaller branch on the ether only has 2 carbons on that side of the oxygen, that's 1 ethoxy pentane. So easy enough. That's actually easier than the alcohols to name. Frankly, right? It's just throw that oxy stem in your regular branches. And so you can see if we're using the systematic name, then we're never going to put the ether at the end. So that's always kind of our lowest priority when it comes to naming.
So it could be methoxy, ethoxy, butoxy.
Yeah, exactly. Cyclopentoxy.
Okay, right on. That's it.
When as we get more functional groups in, we'll actually have to name alcohols as a prefix, with a prefix sometimes. If the alcohol is not the most important group. Like for instance, it's just a molecule I'm making up, it doesn't actually have any relevance really. The acid group is gonna be the most important for naming this, and so we actually need to use a prefix to name to say where the OH group is, and we just say hydroxy in that case. So oxy just means that you have an oxygen single bound to something. So this would be 3-hydroxy butanoic acid. And we see that a lot in pharmaceuticals and in biochemistry as well. There's a lot of times there'll be one version of a molecule, and then there'll be the hydroxy version of that molecule. Or in the case of like ribonucleic acid, RNA, then you have deoxyribonucleic acid, which is just missing an oxygen. Or deoxy, it is. It's missing an OH group, right? Right. So technically it would be dehydroxy, but they didn't keep that for whatever reason. And there's no changing the name of DNA at this point, so. They didn't consult the chemist. All right, so let's practice naming these. That's why it feels like we don't have any floor space. So our parent molecule for A is benzene. And it has a methoxy group attached. I believe that is one that has most of the single substituted benzenes have a common name. I believe this common name is anisole. But I'm not entirely sure, so I'll look that up at some point. Then our parent molecule on this one is going to be dichloro. There's going to be cyclopentane. And if we're choosing between the halides and the ethers, it doesn't really make a difference which one you call carbon one. You probably put carbon one on the oxygen. But that's not gonna be one that there's a wrong answer to really. So, and we would just have, in order to be absolutely clear, I would put numbers on both of them. It's a little redundant, but it keeps you from being ambiguous. So. 1-ethoxy. I was thinking about. Dichloro. And then we just have to assign R versus S. Which we're pretty good at this point, I think, but just for practice. Highest priority. Then the closest way to the carbon, to the chlorines is gonna be second priority. Third priority is the other way around. Then lowest priority is the hydrogen that's already facing backwards.
So you don't have to switch.
So we don't have to move anything around. Clockwise makes it R. So R, 3,3-dichloro, 1-ethoxycyclopentane. The names are long and complicated, but predictable at this point, hopefully.
Does it matter which one comes first as far as the dichloro or the ethoxy?
I mean, technically, you put the dichloro first for alphabetizing, whether you're alphabetizing like D for dichloro or the C for chlorine, it's still before the E, but we're not thinking about alphabetizing. Just gonna check and review. Yes, I'm curious now if I'm remembering that right. Those common names for the benzene, monosubstituted benzenes are not ones that I ever memorized very successfully. So let's see what methoxybenzene is. Building it in Moldia. Nope, I was right, it is anisole. It has a role as a plant metabolite. So it was probably first isolated from anise. The licorice plant. All right, any questions on naming ethers? You think of any weird situations you want to ask about? Not at this point.
There's only two thoughts, go to us.
Yeah.
Yeah. Just
Racist.
So these were called crown ethers. Basically because they kind of look like a crown. There's a lot of up and down in this big, long ring structure. They're a very specific application of ethers, but they're one that there's getting lots of research right now. Because you can basically make like an artificial hemoglobin.
That's what I was about to say, you can make like a coordination compound.
Exactly, so they're designed so that they, well, it's not designed so much as their structure inherently has all these lone pairs. That the most stable geometry puts all those lone pairs on the oxygens all pointed towards the same space. If it's in this ring structure. And so that winds up creating sort of this like little nest of electron density and partial negatives. That is really attractive to anything with a partial positive or a full positive charge. And you can basically, by just changing how many oxygens and how many carbons you have, you can basically custom make the size of that cavity in the middle, depending on what type of metal ion you want to make a coordination compound with. So these wind up being really, really useful. They're getting a lot of research in terms of like drug delivery as a way to sort of keep certain heavy metals kind of sequestered until they get to where they're going in the body. In particular, we see a lot of that with cancer drugs. One aspect of chemotherapy, the whole idea of chemotherapy is to try and kill the tumor.
But you just kill
cells.
everything.
But it kills everything, but the more you can make it so that the chemotherapy drugs are only being released or being contained, the area that has the tumor, makes it so you have fewer adverse side effects. Chemotherapy has actually come a long way from 20 years ago even. As far as those side effects, it's not nearly as bad. I guess for everybody, for some people, it's still just as bad. That's a case by case thing, and I'm not a doctor. But basically, one of the big drugs that gets used is platinum based. Platinum really is really nasty for most of the body, but if you can keep it sequestered and soluble until it gets to the right spot, then you can wind up limiting some of those side effects. It's also a really convenient way to treat heavy metal poisoning. If you put the empty cyclic ether into the bloodstream, then what it's going to do is it's going to seek out metals that fit in there. Basically, and then they're going to stick together in this complex that allows it to the metals to not get stuck in proteins and things like that, allows the body and the kidneys to get rid of it a lot more effectively. The classic and the cheapest way to do this is with EDTA, which is,
I remember that, yeah.
it's ethylene diamine tetraacetic acid, which is, so it's ethyl with two amines, so those each have a lone pair, and then attached to each of those is an acetate group. And then the same on this one, so you wind up with a whole bunch of lone pairs and enough movement in all these bonds that they can kind of like, almost like a claw machine at the arcade. They kind of surround a heavy metal ion and keep it soluble and keep it moving through the body. And that actually so they call that chelation therapy when you're making a coordination compound, is also called the chelate. The chelate is the part that is the negatively charged part of it. So it actually gets prescribed a lot in hospitals anytime there's heavy metal poisoning. But for a while, it was actually like a gimmick, sort of a fad, health fad, where you could actually
Detoxers.
a detox by having an IV of EDTA was actually, you could actually go to, they had places in Reno that really like specialized in get over your hangover, where you could get an IV bag of EDTA to detox.
Give us $1,000 and your hangover will be cured.
Right. The problem is if you don't actually have heavy metal poisoning and you get chelation therapy, you actually start pulling the metals that your body wants out, like iron There's a role for, for copper, manganese and stuff like that in the electron transport chain. And so you wind up pulling that out and making yourself anemic if you're not careful. Not to say you have to go to the doctor to get a prescription for everything, but I'm very skeptical of people that suggest IV bags that don't have medical advice.
Yeah, I don't know, I've always found that to be very interesting.
And if you're just doing it to rehydrate or something like that, that's one thing, I suppose, but still, you put some, you're putting something directly into your body, bypassing your liver and your kidneys, you're running a pretty big risk in trusting them about whatever's in there.
Like, I would understand if you're nauseous and you couldn't really hydrate yourself, but just doing it
Yeah,
with an IV, not like.
I don't know, too bad David's not here, I'm sure.
Would have something to say.
Would have something to say about that. Anyway, needles, I don't like needles anyway, so it's not a big. So one of the aspects that this affects synthetic chemistry is it actually does allow us to fluorinate things pretty well. Fluorine is not a great nucleophile normally, because in protic solvents, it gets surrounded by the solvent molecules too effectively, right? And remember how that kind of kept it sequestered and made it so it wasn't a good nucleophile? And it's polar enough, or it's a strong enough charge that it also won't really dissolve in nonpolar solvents. So we've never been able to actually use fluoride as a nucleophile. But this is one way to encourage fluorine to be a nucleophile, is use a nonpolar aprotic solvent with the crown ether in it. Because the crown ether is going to stabilize the positive ion out of your ionic compound without stabilizing the fluoride. So that allows you to make these, to basically get fluoride to dissolve in a nonpolar solvent, and therefore it can be a pretty good nucleophile in that case. Don't worry too much about the making of the crown ethers. You basically pick those names are have to do with the second number is how many oxygens there are. The first number is the total number of atoms in the ring. So this is a 12-sided ring of which 4 of them are oxygens. 5 crown 15 or 15 crown 5 means 5 oxygens and a total ring that has 15 atoms in it. And basically you're just going to change the size depending on the size of the metal ion you want to interact with. The bigger the metal ion, obviously, the bigger the crown ether.
So the fluorination example, how toxic would that be in terms of like just doing it in lab?
I don't think it would be too bad. This is just sort of a specialized thing we'd have to order, the crown ether.
Right, exactly.
But I actually don't think it's far enough. A lot of times stuff that doesn't really occur in nature is not actually that toxic to us if it doesn't look anything like what occurs in nature, unless it's going to do something like disrupt cell membranes. Like your body doesn't really have any way of processing that because it's not something that would ever really occur. So I don't know. I think probably the benzene itself might actually be the nastiest thing that presents a pretty strong carcinogen.
Size of the molecule is potentially getting the way process.
The size of the molecule has potential to get in the way
Like certain processes.
in the body.
But
Yeah, potentially,
enough
if enough is consumed, and you can wind up with that issue where you pull the metal out and become anemic, like the EDK example we were just talking about. So yeah, you can definitely interfere with some processes potentially, but it's not something where I would think like, oh man, if you get one whiff of that, you're a goner, necessarily, like some of the compounds we talked about.
so yes.
Exactly. Alright. If we wanna make ethers. The simplest version, the original version of the synthesis was basically you take primary alcohol and you just heat it with a strong acid. And if you do that, you get this equilibrium process where your primary alcohol will wind up dimerizing, basically you stick two of them together. And you dehydrate the alcohol and you connect the two pieces to make an ether. So proton, it's acid catalyzed, so first step is a proton transfer to your alcohol to make it a better leaving group. And then you have another molecule of the alcohol act as a nucleophile, and your water act as a leaving group. And then we just do one more proton transfer. The yields aren't great though. And it only works because this is an SN2 step. And this is not a strong nucleophile. You really only see it with primary alcohols. And you only reliably use it to make symmetrical ethers. Because it relies on having another molecule of alcohol around to dimerize. So if you tried to do this with a mixture of two different alcohols, they were equal molar amounts. In theory, you could do that, but you're gonna get 4 different products, 3 different products. So that you're limiting your yields to 25%. If you're trying to make one of those non-symmetrical ethers. Alright, so what this is a good mechanism for us to remember, just because this is a really common thing that happens all the time. And we're gonna see the opposite of this happens if you take an ether and you put it in acid, the reverse reaction will happen. But the more predictable way to do this is what's called the Williamson ether synthesis. And it works, it's a mechanism we've actually seen. You start by deprotonating the alcohol. You deprotonate one alcohol, and then you use it as a nucleophile on a halide. So by controlling where the halide is, or what your halide is, this is a pretty reliable reaction. And pretty versatile if we're trying to make an ether, with one exception. This alkyl halide, it has to go through an SN2 to get replaced, right? So what limitation does that inherently put on the red one? It can't be, what will not go through an SN2? Think about your reactivities.
Well, kind of like a big bulky base, wouldn't,
A big bulky, strong base. So we're making a strong base.
right,
And the bigger the R group is, the slower the reaction is gonna go. But the red R group also can't be tertiary. Okay. Right, because you can't have an SN2 reaction with a tertiary halide. And so we're still somewhat limited. But our mechanism is exactly what it sounds like. Remember, the sodium hydride deprotonates an alcohol irreversibly because we made that hydrogen gas in the leaving group that leaves the whole system. And then we add the target for our nuclear attack, our nucleophilic attack. Right, so both the red and the blue are somewhat limited by sterics. The bigger our groups are, the less this is going to work. But it's more important, if you have to pick one of these to be a tertiary, you probably want to do the blue one, not the red one. And then, even then, though, you still have to worry about actually having an elimination reaction happen instead of as a side reaction. But we can usually get at least some product. And this also means, but just like we saw before the Grignard reactions too, this means we can actually flip flop what's the red one and what's the blue one, kind of however we want, whatever makes sense with sterics. Right, because it doesn't really matter which one started as the alcohol, which one started as the halide, because we're making an ether out of both of them in the end anyway. So that gives us a lot of flexibility with which one's the red, which one's the blue. Right, and so that also means we're trying to make, this is a really common gasoline additive, MTBE, right? Did we talk about this one back in
We used it as a salt.
We used it as a solvent, right? We want to make MTBE, big bulky group on one side of our ether, right? This pathway doesn't work. We can't start with methanol and the tertiary iodide because this tertiary carbon is too big. Yeah. So we're not gonna ever put a tertiary group as the halide. If we have to use a tertiary group, we're gonna put that as the initial alcohol. And the smaller group as the halide. Which means we're still somewhat limited by this. We can't make di-terbutyl ether using this pathway. But as long as all we're dealing with is primaries and secondaries, we actually have kind of free reign to set this up however we want. Just like with the Grignard reagent where there's multiple pathways to get to the same product. All right, let me. We do a couple more slides. Then there's 2 slides of practice problems. So if we do a couple more slides now, then we can break until lab and have a longer gaps for lunch. Is everybody okay with that?
What's the lab gonna be today?
I think, I actually got the order mixed up, so I think it's one's not as relevant, but I think that it's we're gonna brominate cinnamaldehyde. We're gonna start with cinnamaldehyde and brominate
I
it.
like good smelling stuff. Okay.
And I believe we got this procedure working well, but it gave us trouble at one point because of resonance that I didn't account for. So we'll try it. At the very least, it'll smell good. Then we'll go from there. All right. So we're trying to use a Williamson ether synthesis to make this molecule, ethoxybenzene. What are the 2 options that we could use? Or we got to start with one of our R groups as an alcohol and one of our R groups as a halide. We could start with phenol. So we could do and then that's going to react with sodium hydride in step 1. Step 2 then would be ethyl iodide. We can start with ethanol. Have it react with sodium hydride. And then our second step just has to be, bromobenzene, a common one. We see any problems with either of these? Anything that would favor one over the other?
I think the first one we did definitely favor.
Why?
Books. Just because of the halide that we're using, that benzyl bromine.
Bromobenzene is
So huge that like.
it's massive, and there's aromaticity involved, right? Which means that that's not necessarily actually a good target. Because we
It's
don't
gonna be a
usually
lot harder
do-
for it to actually pop off compared to just ethyl iodide.
Yeah, we can do what's called electrophilic substitution with benzenes. But they aren't really good targets for nucleophilic substitution because of all that electron density. So this one would actually work better, practically speaking. They both work fine in terms of, like, I'm pretty sure we have. Like, the only thing up here that we might not have in the stock room is, I'm not even sure if we have sodium hydride, but we could use sodium borohydride instead potentially. So this one would probably work better because I know we have phenol, and I'm pretty sure we have ethyl iodide. I know we have bromobenzene, and I know we have ethanol, but we have that other wrinkle.
I remember like 50% yield, it would give you something else.
It would give you, you'd have some other side reaction in all likelihood. And I haven't reviewed that chapter yet, so I'm not gonna speculate, I don't know the aromatic reactions as well off the top of my head. All right, last reaction. Basically undoing this. This is what I mentioned earlier. You can take an acid and 2 alcohols and heat them to make an ether, but you don't get great yields. You do the opposite, especially if you use a halide acid. You can actually turn an ether all the way back to the original halides. And you're basically just gonna do a couple of protonation, leaving group leaves, substitution reactions. And this overall process is called acidic cleavage. Interestingly enough, acidic cleavage is also what you get when you put a starch in an acid and heat it. Because starch is just a whole bunch of glucose molecules that are linked as ethers. So if you put it with an acid and you heat it, you wind up breaking up the ethers into glucose molecules again. And if you continue that process, you wind up with some other substitutions out there. But if you took honey is a dimer of fructose and fructose, I think, links to fructose molecules, but I might be wrong about that. If you heat it in with a twist of lemon, you actually wind up breaking the honey apart and you wind up making corn syrup, basically. You wind up making a mixture of glucose and, maybe it is glucose and fructose. Blanking on it right now, it might be 2 glucoses. Side point, it's the same process, a little bit of acid and heat causes these larger sugar molecules to break up into smaller sugar molecules. Because you're breaking apart the ethers.
So starches.
No starch in ceviche, right? Alright, so our mechanism here is gonna look like this. It's drawn as two steps. You're gonna make the first alkyl halide, it's just, you take your ether and you protonate it. Acid catalyzed, right? And then you have a halide around that connects to the nucleophile and you've got a good leaving group. And then you just do the same thing again. The second step is you take the alcohol that's left over after the first step, protonate the alcohol, making a good leaving group. And that gives you another nucleophile that can come in and replace it. Why is it critical that we heat this for this to work? Are either of these reactions that would really happen that well at room temperature?
No, it's the entropy.
It's the entropy thing. Because in this case, even if we protonate, the oxygen is still not a great leaving group, and our nucleophile is not a great nucleophile. Right, so for this to happen, we have to have that entropy piece driving it forward. And if I get back to the net reaction again, if we stop halfway, we wind up making something that's going to stay dissolved. One of your nucleophiles is going to stay in solution because it's charged. So by having the reaction happen completely, if we heat it enough, we get 3 volatile products out of it, as opposed to a solution and a single volatile product. So it's really the entropy piece that drives this one. And it is, to some extent, reversible. Because if you think about reversing this, you're taking a water and using it as a nucleophile on one of these halides to do an SN2. We saw that back when we first did SN2s, right? Water's not a great nucleophile, but it's good enough if you have a bromide as a leaving group. And then you have that alcohol that you just made can then act as a nucleophile over here. That first ether synthesis that we looked at, the acid catalyzing their synthesis, was literally just a halide and an alcohol with water or with heat. Right, so we're not going to get great yields either direction with that because it's an equilibrium process. But we can get some product that way. And so it's one of those reactions where sometimes just using Le Chatelier's and some brute force and being okay with mediocre yields winds up being enough for an industrial process if you don't need it to be 100% efficient. All right, since we've added a lot of reactions in the past week and a half, the second half of this lecture, I'm just going to give you time to go practice with some of these. I have just a couple slides of practice reactions, some with ethers, some with the alcohol reactions. And I'll go print those off real quick so that everybody has a copy of them. And we can go through any of them that you have questions on. I don't think we'll turn it in as an assignment. It'll just be, it'll give you free time to go practice, go eat some food, and be ready for lab at 1. All right, everybody good if I take this down to go print? Christine, you have the slides up on your phone?
Yeah.
Okay.
I will in just a second. Actually, let me grab my keys and we'll